Hi everybody, this is Dr. Bricker here with a introduction to reflection and refraction P&W. So it looks something like this. So this deals with reflection of light and refraction of light. So reflection of light is a ray of light coming in, hitting a smooth surface, uh, and reflecting in a nice way. So not diffuse refraction, a nice smooth reflection. And refraction is the bending of light. So when light goes into a lens, something like that, into a material, light is bent. So refraction is the bending of light. Okay, so there's a few parts to the lab. So you see in this picture here, here's an incident ray of light coming this way. Here's a reflected ray of light. So the first part of the lab deals with reflection. So remember that all of these angles are measured to the normal. So if this is a mirror, here's 90 degrees to the mirror. So normal to the surface means at 90 degrees to the surface. So the incident angle is this angle here. So that's the angle measured relative to the normal. The reflected angle is this angle here. So also measured with respect to the normal. So you got a couple of multiple choice questions here. Which is the angle of incidence? So this is the incident angle. Which is the reflected angle? So you have a couple of free points coming up here. Okay, good. So once you answer those, you could hit lock answer and continue. And then you can go to the reflection section. And here you'll see a video, and you've got a tool here, so you could add this protractor, move it to wherever you want to. Okay, and I'll make the screen a little bit bigger. So you can take the protractor and move it to wherever you want to. I'm going to put it right here in the center. And I can step through the video just by hitting the step button here, and you'll see what's going to happen in just a minute. So here's a laser pointer, and here's a ray coming in. So there's an incident angle measured relative to the normal again. So the incident angle would be whatever this turns out to be. And then there's going to be a reflected angle. And again, they're going to spray some substance. You'll be able to see the laser beam a lot better in just a minute. I'm just stepping through the video. And here's the spray. Okay, so you can take more time and get this in here carefully. Let me actually advance it so the person's hands out of the way. Just doing frame by frame. I think it'll be out in just a second. Maybe you have to just leave it in. Let's see. Maybe something like that. Okay, so I set this up pretty nicely, and you can see the incident angle. That's this angle relative to the normal. You have to do a little bit of estimating. What is it, about 16 or so? And then you can look at the reflected angle. Again, measured from the normal. This is from the normal. Same thing, it's about 16 degrees. So when you go through here, you'll see there's a relationship between the incident angle. Again, here, this is the incident angle, and the reflected angle. Okay, so play around with that a little bit, and you have the protractor to work with, and you'll be able to record these things. So angle of incidence goes here, angle of reflection goes here, get at least 10 measurements. And when you do that, you'll build a nice graph, and you'll be able to see how the angle of reflection and the angle of incidence are related to each other. You already have an idea, and from class you know that those really should be equal to each other, so you should get a nice line here. Okay, so there's a few questions to answer here. How do the angles of incidence compare to the angle of reflection? Just be careful again, it's the angle measured relative to the normal. So you shouldn't have any negative angles, anything like that. You know, it's relative to the normal. So if it's 30 degrees this way, that's 30 degrees. If so the incident angle is 30, for example. If the reflected angle is also 30 degrees, it's just 30. So, you know, the angles go between like 0 and 90. No negative angles, nothing big. It's all relative to the normal. Okay, so you'll have some questions to answer there. Okay, and then once you answer those, then you hit lock answer and continue, then we'll get to the refracted section. And you, of course, you'll answer the questions. So refraction is the bending of light. And we're going to see another video here. And there's a laser beam here. It's going to hit this interface at different angles, and the light is going to be bent. So I'll just kind of step through here. Actually, let me make it a little bigger. And I can step through here. And the same thing, they're going to have to spray some substance so you can actually see this. Okay, so I just paused it at that point. We're going to have a nice sort of protractor here too, and we could put it right at the interface of the surface. You can take more time than I'm doing. And now you can definitely see that the light has been refracted, or in other words, bent. So the same thing, there's going to be an incident angle. So this is just air up here, index of refraction of 1. So this is the incident angle. So you've got 15, 30, 35, 36, 37, maybe like 37.5 the way I have it set up here. So this is the incident angle, this angle here. And then here is the refracted angle. So that would be like 15, 20, 21, 22, probably pretty close to 24. So the incident angle and the refracted angle are different here. So this behavior is governed by something called Snell's law, and we'll see that in just a minute. Okay, so you've got the video and you've got the protractor tool that you could use, and you're going to measure the angle of incidence, and this will automatically calculate the sine of that angle, and then you'll be able to measure the refracted angle just like I just did, and then this will calculate that for you. And the same thing, we're going to get a nice graph here. So this is the sine of the angle of incidence. This is the sine of the angle of refraction. And we're assuming that the index of refraction of the air is just 1. Okay, so fill out this data table here. This will create the graph for you. And again, it won't be the same thing that you got in the first part, because the angle of incidence is not equal to the angle of refraction. And again, the behavior is governed by Snell's law. So make the graph, and from the data table, it'll be populated for you. That's 10 points right there. Make sure you do all 10 points. From the data table, what do you notice about the angle of refraction? How the angle of refraction changes as the angle of incidence changes? And is it the same as the last one? So once you make the graph, you'll be able to answer that question. You have pre-populated sine, angle of incidence, sine of angle of refraction columns calculated from the angles that you measured. Take note of what is plotted, so take a look at the graph. Include a linear curve fit of the graph, and then what is the slope of this line? So the same thing, once you get your graph, you can put equation of the line on there and get the slope. So why do you need to get the slope? Let's take a look at that. Okay, so your data you'll have graphed over here on the vertical axis, the sine of theta incident, and over on the horizontal axis, the sine of theta refracted. And then this is Snell's law. N incident sine of theta incident is equal to n refracted times the sine of theta refracted. So once you plot this, you'll put the equation of the line on here. So what does the slope actually represent? So let me divide both sides by n incident. I have this then. N refracted sine of theta refracted divided by n incident. Now when you plot something like this, and we've done this before, this looks like y is equal to mx. Not my best m of my life. mx. So when you have something on the vertical axis and something on the horizontal axis, so the vertical axis is the sine of theta incident, the horizontal axis sine of theta refracted, whatever comes in front of that is the slope. So this is like y, this is like x, so the slope turns out to be n refracted divided by n incident. But don't forget N incident is just air. So if N incident is just air, so that's 1, the slope turns out to be the index of refraction. So that's something greater than 1. So that's really the goal of this. Once you plot sine of theta incident versus sine of theta refracted, you put the equation of the line on there, the slope will be the index of refraction. Okay, and it's got to turn out to be greater than 1. Okay, so back to this. So from Snell's law and the little bit of algebra I did, what is the slope? Well, you just saw what the slope represents physically. And then you'll get a value for that. And then the actual index of refraction of the material in the video is 1.5. So the index of refraction of glass is around 1.5. How does your value compare to this? Is it greater than? Is it more than? What's the percent difference between this and the actual value? So how far away is it from the actual value? And if you forgot the formula for this, you'll need to look it up. So figure out the difference between those two and then divide it by how much it's supposed to be times 100. So anyway, look up percent difference. And then the last question here, how could measurement error have impacted your value? So that goes along with this whole idea of you are doing some estimating. Is it 18? Is it 17 and a half? That sort of thing. If you're working for NASA, you would not use just a protractor to do this. You'd have a more sensitive piece of equipment, or maybe you'd have a better video so you could really see where those lines are. Okay, and then explain specifically how measurement error could or could not have caused this percent difference. So you should have a pretty close answer. If you get something that's like 30% off, maybe you've done something wrong. Okay, so have some fun with it. This is a little more straightforward of a lab than the first 4, I think. And I will talk to you soon. Bye-bye.